This video is an introduction to PBA.pro's latest feature, automatic C source code generation. It will allow the user to set up a mil standard 1553 bus controller or remote terminal configuration within PBA.pro, taking advantage of the convenience and rapid development offered by PBA.pro. Then, after the configuration is working as desired, PBA.pro can create a standard C program file which can be compiled into a program that will directly control and manage AIM's 1553 hardware without ongoing need for PBA.pro. This capability is relevant for a variety of goals and efforts, such as rapid prototyping, full development for custom or embedded applications, debugging and maintenance, familiarization, guidance, and education concerning AIM's application programming interface, and more. In this video, we will show all the steps. So besides being an introduction, it is something of a tutorial as well. We'll start with a clean slate and set up a basic bus controller which will emit a simple set of messages, one at 10 Hz and another at 3.33 Hz. We bring up the transfer list and add one command that instructs remote terminal number 1 to send messages to the bus controller at 10 Hz, and remote terminal number 3 will be commanded to receive messages from the bus controller at 3.3 Hz. Setting the minor frame time to 100 milliseconds will cause each minor frame to go out at 10 Hz. For simplicity, we will have the bus controller only emit 3 major frames, so the end times variable is set to 3. Now we set up the framing by having 2 different minor frames, called A and B. Both minor frames will contain the first message, the one that goes out on the bus at 10 Hz, and only minor frame B will have the second message, which goes out at 3.3 Hz. And the major frame will be set up to consist of 3 minor frames, A, and then a second A, followed by B. This AAB pattern of minor frames will be repeated once for each major frame. We're ready to try out the bus controller commands to be emitted by the main demo computer with a separate helper computer acting in the role of bus monitor. This lets us see what is happening on the 1553 bus. The message analysis graphical display shows message number 1 going out on every minor frame, i.e. 10 Hz, because each row represents 100 milliseconds. And message number 2 goes out once every third minor frame, which is 3.3 Hz. The pattern shows the AAB sequence of minor frames described earlier. But there are no responses to any of the BC commands because this particular 1553 bus doesn't have any active remote terminals. That is why this table showing BC commands is highlighted in yellow. It's a warning that remote terminal responses, which are required by the mil standard 1553 rules, are absent. However, the separate helper computer, acting as a bus monitor, also has the ability to simulate any number of remote terminals. So we'll quickly set up a couple remote terminals to respond to the bus controller. OK, PBA.pro makes quick work of that, so now we enable the remote terminals just created. Now the main demo computer, remember the main demo computer? It can run the bus controller profile, and this time there should be RTs out there responding to each command. The table with the BC commands is shown on a white background, which means the remote terminals have provided responses as required. The message analysis graph looks a little different than before due to all the remote terminal activity in response to the BC commands. Now for the C source code generation. It takes only a second or two. Here's a Windows command session where we can see the C source file that was just created. See the bcexample.c file? And the runcl.cmd file is a script that will compile the BC example into a standalone program. This command in the Windows session will compile the program. We'll set up the helper computer to run the bus monitor again, and the remote terminals are still running. Now we run the BC example program and it will make the bus controller and the AIM-1553 hardware emit commands exactly as PBA.pro did earlier. It only took a second. Let's check the bus monitor over there on the helper computer. There it is. The message analysis graph shows exactly the same behavior from the C program as we saw when PBA.pro was running. In fact, let's shut down PBA.pro on the main demo computer and run the BC standalone example again. Okay, reset the bus monitor again and run the example in the Windows command session. We'll rearrange the screen so the bus monitor over on the helper computer can be seen at the same time as when the BC example program is run again. And there you see the bus monitor has once again recorded the bus traffic that we have set up. Now what if we want to program some remote terminals instead of a bus controller? We can do that by switching roles between the main demo computer and the helper computer. PBA.pro on the main demo computer can receive the bus controller commands from the helper computer. Okay, on another screen I'm starting the BC on the helper computer, and we should see the commands show up in PBA.pro on the main demo computer. There they are. The message analysis graph shows the BC commands that have arrived, and at the moment, the main demo computer is not simulating any remote terminals. So we will set up some remote terminals here in about 10 seconds. And now we reset the bus monitor and enable the remote terminals that were created a moment ago. I'll go off screen and run the bus controller again on the helper computer. Okay, all the message traffic was recorded by the bus monitor, and everything looks normal in the message analysis graph. So now that the RTs have been set up, let's generate the C source code to do the same thing. Now we will go to the Windows command session and compile the RT example program just like we did for the BC earlier in the video. There's the rtexample.c file that was generated a few seconds ago, and here's the command to compile it into a standalone program. Now we shut down PBA.pro on the main demo computer in preparation to use the RT example program to do exactly what PBA.pro was doing. Here is the helper computer. It will be the bus controller and also the bus monitor. So we get the recording display situated on the helper computer screen and start the bus monitor. As a test, we run the bus controller alone on the helper computer and we see the bus monitor table in yellow background, meaning no RTs out there are responding. Back in the Windows command session, we will start the RT example program. Okay, it is running and waiting for some BC commands, so we'll run the BC on the helper computer to give the RT example program some commands. And now the bus monitor records the bus traffic along with the expected RT responses from the RT example program. For your convenience, here is the runcl.cmd script file with the syntax highlighting, which makes it much easier to understand. And while we're here, why not have a quick look at the C source code which PBA.pro generated. Here is the BC example source file. There are a few lines of code here, but it's all very simple, and the main program is streamlined and intuitive. The RT example program is very similar, simple code, streamlined, and intuitive. This video has enough detail that you should be able to duplicate it if you want, allowing you to review all of the C source code or create your own with ease.